Welcome to this lecture. This is the third lecture of week 6. In this week, we are looking at pointwise limits of distribution functions, and by looking at such limiting functions, we have focused on a new type of convergence which we have called as weak convergence. And using this type of weak convergence for distribution functions, we have extended this notion to probability measures on the real line and also for random variables. So far, we have listed some equivalent conditions for this type of weak convergence for probability measures. What we are going to do? We are going to first go ahead by assuming that these equivalent conditions are true and derive some properties of weak convergence. In this lecture, our focus mainly will be these specific properties. So, let us go ahead and discuss using the lecture notes. So, let us set up the notations and the basic ideas. So, we are going ahead with looking at this weak convergence of probability measures on the real line and the weak convergence of that, and also for the same type of convergence for random variables. Now, this type of convergences, as already pointed out, is defined through the corresponding weak convergence of distribution functions. Now, using the corresponding equivalent conditions which we have stated, but not proved so far, what we are going to do is to look at some important properties of the weak convergence. So, here let us start by observing this important fact that if we start with a sequence of distribution functions on the real line and assume that they converge weakly to some distribution function f, but then suppose we are interested in the limiting behavior and whether this limit is unique or not. So, let us assume that the same sequence also converges to another distribution function which we denote by g. So, we have two possible limits which are both distribution functions and we have denoted them by f and g. Now, here by definition the weak convergence will tell us that this pointwise limit will be true for points small x where the limit function capital F is continuous, and also for the second limit that we are considering, again for that we will have another such limiting operation being true, but for those points y which are continuity points of g. Now, suppose we are going to look at the corresponding set of jump points of the distribution functions f and g. Now, this set of jump points will be either finite or countably infinite. So, let us denote them by d subscript f and d subscript g. Now, here let us focus on the complement of the union of these two set of jump points. So, on the complement, both capital F and capital G are continuous, and if we appeal to the definition of weak convergence, we will have that the limiting behavior will give us these specific values at the limits, and therefore, the capital F and capital G must match on all such points. But now, let us focus on the jump points. So, if we look at any jump point of capital F or capital G, it is now an element of this union, and since both of df and dg are either finite or countably infinite, the union is also having the same property that the union is also either finite or countably infinite. And consequently, if we remove those points from the real line, that set turns out to be dense in the real line, meaning if we take any arbitrary real number, then I can approximate these real numbers by points coming from the complements of the jump points. So, now if we use the right continuity of the individual distribution functions f and g by approximating any arbitrary real number x from the right, we can get the equality now extended for all points on the real line. So, we already have established the equality for point small x coming from the complement of the union of the jump points. Now, we are just extending it by right continuity of the individual distribution functions capital F and capital G, and just saying that the equality must actually hold for all points on the real line. So, this is going to show the uniqueness of the distribution function which appears as a limit of distribution functions, but in the sense of weak convergence. So, if you have a sequence of distribution functions converging weakly, then the corresponding limit, which is some distribution function which we are considering here, must be unique. So, this is a very important observation which we are going to extend to the notion of weak convergence for probability measures on the real line and also for the case of random variables. So, let us see. So, we start by looking at these uniqueness properties involving the weak convergence of probability measures on the real line. So, let us start by looking at some sequence which we denote by mu n. So, this is some sequence of probability measures on the real line. Suppose they converge weakly to probability measure mu, but also assume that they also converge weakly to another probability measure nu. What we would like to claim that these two measures must match, in the sense that for all Borel sets the size of A or the probability of A should be same in the mu measure and the nu measure. So, mu and nu must match for all Borel sets and therefore, mu equals to nu. So, this is our conclusion that we would like to derive, and a similar property is true if we are going to look at a sequence of random variables. So, again let us set up the notation. Suppose x n is a sequence of random variables defined on possibly different probability spaces. Remember, even if the x n's are defined on possibly different probability spaces, we can still consider the weak convergence of such sequences of random variables and assume here that they converge weakly to random variables x as well as y. All right. Then the conclusion is x and y have the same law, meaning the distribution of x and the distribution of y must be the same. Stated another way, the probability measure induced by x and the probability measure induced by y, they must be same on the real line. So, let us see. So, first we consider the case involving the sequence of probability measures converging to the probability measure mu as well as nu in the sense of weak convergence. As per our definition, we are supposed to look at the corresponding sequence of distribution functions. So, let us denote the corresponding distribution functions like this, that f denotes the distribution function of mu, g denotes the distribution function of nu, and f1 f2 so on denotes the distribution functions of mu1 mu2 and so on. Since we are assuming that mu n converges weakly to mu as well as nu, then by definition f n must converge weakly to capital F and as well as weakly to capital G, and therefore, by our previous remark we must have the distribution functions f equal to the distribution function g. But a distribution function uniquely identifies the underlying probability measure, and the distribution function f corresponds to the probability measure mu, the distribution function g corresponds to the probability measure nu. Therefore, we must have that these two probability measures agree on the real line, meaning for any two Borel sets mu of A must be same as nu of A, and that is the statement we wanted to prove. Alright. So, let us now consider the same version for random variables. So, here what we assume is that x n converges to x weakly as well as to y. Now, as per definition, the law of x n's will now converge weakly to the law of x as well as to the law of y. Alright. So, here law of x n denotes certain sequence of probability measures on the real line, and that is converging weakly to the law of x, which is a probability measure on the real line, as well as to the law of y, which is again another probability measure on the real line. But now, we can just go back to our previous statement. So, by part 1 we will claim that the law of x must be the same as the law of y, and therefore, x and y are equal in law or the same in law, or x and y has the same distribution or the same law. So, this completes the proof. So, this is a important characterization or an important property of weak convergence, that the limit is unique in a certain sense. So, if you are considering the case involving distribution functions, then the limit is pointwise unique. If you are considering the weak convergence through probability measures on the real line, then again you must have a unique probability measure as a limit. However, if you are considering the case of random variables, you have to be slightly careful. The limit is unique in the sense of law, meaning if you have two random variables x and y being the limit, then they are equal in law. So, here we would like to clarify whether we can talk about pointwise equalities for random variables. And here there is this very important cautionary statement that we are going to discuss. Let us see. We are going to talk about this specific setting, that we are focusing on weak convergence of random variables. So, first of all, in this situation we already understand that random variables may belong to different probability spaces. Therefore, the limit that we are considering, the let us say the random variables x as well as y, they may be defined on different probability spaces, and in this case if they are defined on different probability spaces, we are not able to talk about pointwise equality of this limit random variables. However, let us assume that we can talk about the limit random variables on the same probability space. So, if we assume that, then we can again ask the same question, whether we can talk about the pointwise equality of the limit random variables. So, we are going to discuss a explicit example that will tell us that that is in general not possible. So, the best result that we can say in general, that the limit random variables must be equal in law, but not necessarily pointwise. So, let us look at a explicit example to illustrate this point. So, we are starting with a random variable x defined on some probability space with this Gaussian law. So, I am looking at a standard normal random variable with mean 0 and variance 1. So, suppose I take such a random variable capital X and define another random variable on the same probability space by looking at minus x. So, we are now calling minus x, just for our notational convenience, as y. Now, by the symmetry of the random variable x about 0, or equivalently the symmetry of the standard normal distribution about 0, we claim that y also will have the same distribution, meaning y will also follow standard normal distribution. Now, in this case we construct a explicit sequence of random variables again on this same probability space defined as follows. So, for positive integers n, when it is odd, we will take the sequence x n to be equal to x. If n is even, I will take it to be y. Now, it is immediate that all the random variables that we are considering have the distribution with standard normal distribution, and therefore, their corresponding distribution functions are also same. Therefore, we immediately conclude that x n's converge to x as well as y. But you note that if we are asking for the pointwise equality of the limit random variables, let us look at this. So, we are asking for the probability of the event that x is equal to y, but if we put y equals to minus x, then this event is equivalent to the fact that probability of x is 0. So, this event is equivalent to the fact that x equal to 0, and the probability of that is 0 because x is an absolutely continuous random variable, and therefore, we immediately have the probability must be 0. So, therefore, we cannot talk about pointwise equality of the limit random variables even if they are defined on the same probability space. So, we will have to be careful while talking about such equalities. We can only say that when you are considering the weak convergence, the equality holds in the sense of law. All right. So, now we go back and look at another type of a interesting property which we considered for earlier modes of convergences. In particular, we have discussed these three types of modes of convergences: almost sure convergence, convergence in LP and convergence in probability. We mentioned that for almost sure convergence and convergence in probability, continuous mapping theorem holds. The continuous mapping theorem states that if you have a continuous function on the real line, then compose with a given convergent sequence of random variables, then the resultant new sequence of random variables must also converge in the same mode of convergence, meaning either the almost sure mode of convergence or convergence in probability. However, we have also commented that continuous mapping theorem need not hold for convergence in LP. We are going to consider a similar question for weak convergence. So, here what we are asking is that suppose we have a weakly convergent sequence of random variables and we apply a continuous function on top of it. Can we say that the resultant sequence of random variables will also converge? So, this is the next theorem. Let us see. So, we are starting with assuming that a sequence of random variables x n converge in law or in distribution or in the sense of weak convergence to the random variable x. Then the statement says that if we take any continuous function denoted by g from real line to real line, then the resultant sequence of random variables denoted by g of x n must converge in the sense of weak convergence to g of x. So, this is the continuous mapping theorem for weak convergence of random variables. All right. And to do this, what we do is that we go back to our earlier equivalent statements that we have already pointed out for weak convergence. We are going to make use of those equivalent conditions. Remember, we are yet to prove those statements, but we are going to use them and we will come back to the proof of them in a later lecture. All right. So, now if we go back to those equivalent statements, one of them suggests that it is enough to check that for all bounded and continuous functions small f, we show that small f applied to g of x n, if I look at the expectation of that, that should converge to expected value of small f applied to g of x as n goes to infinity. So, here we are asking about the weak convergence of g of x n to g of x, and this is equivalent to having this star relation holding for all bounded and continuous functions f defined on the real line taking real values. So, now if we look at any such bounded and continuous function f, we first observe that the function h defined as the composition of f composed with g must be bounded and continuous. Why? Because first of all, both f as well as g has been assumed to be continuous. So, the composition is continuous. However, the continuous function f is bounded and therefore, the composition must also be bounded. So, therefore, any such function h which is f composition with g must be bounded and continuous. Now, what we do? We apply this equivalent characterization of weak convergence that we discussed earlier in remark 6 to the bounded and continuous function h. So, here we start by observing that as soon as x n converge weakly to x, then expected value of h of x n must converge to expected value of h of x as n goes to infinity. But this is the exactly the relation star which we wanted to prove, and therefore, what we have ensured is that for all bounded and continuous functions small f, the star relation holds, and hence we must have g of x n converging weakly to g of x, and this proves the continuous mapping theorem for weak convergence of random variables. All right. So, this is an important observation and has very nice applications. One quick application is discussed in this note. What we do is that we fix two real numbers a and b, and here we consider explicit continuous function, let us denote it by again by g, given by this affine function. So, we are sending any real number small x to a x plus b. So, this is a nice continuous function, and therefore, if we apply the continuous mapping theorem for weak convergence, then for any weakly convergent sequence of random variables x n converging to x, we must have a x n plus b converging weakly to a x plus b. This is a very simple application of weak convergence. We can also apply any of our favorite continuous functions and get the relevant continuities. So, for example, if we appeal the same theorem, the continuous mapping theorem, to the square function, then we will also able to conclude that x n squared must converge to x squared. A similar type of conditions will be true, let us say if we appeal to the sine function and look at the new sequence of random variables given by sine of x n, and that will converge weakly to sine of x. So, we can appeal to any of our favorite continuous functions and get the relevant convergence in the sense of weak convergence. Alright. So, now again going back to other three modes of convergence, we have seen that both the convergence in LP as well as the onward-Schur convergence imply the convergence in probability. Now, we are going to compare these three types of convergence with this fourth type, which is this weak convergence. However, it is important to note that the earlier three types of convergences were considered on the setting of same probability space, meaning if we are considering these three earlier modes of convergence for some sequence of random variables, they must be defined on the same probability space. However, in this fourth type we are allowing a relaxation, but if we want to compare these earlier three modes with the fourth type, first of all we have to come to the same page, which is what that we have to first take the sequence of random variables coming from the same probability space, and only then we will be able to compare this fourth type with the earlier three types. And towards this direction, this is our next discussion. Alright. So, what we first do is that we start by looking at some sequence of random variables given by x 1, x 2 and so on, and assume that there is a limit random variable x in the sense of convergence in probability. And this statement says that if you have convergence in probability, then x n must converge weakly to x. So, therefore, what we are concluding that convergence in probability implies convergence in the sense of weak convergence or convergence in distribution or convergence in law. Okay. So, again we will go back to one of our equivalent conditions that we have been using for testing weak convergence. What we want to show is that for bounded and continuous functions, we want to establish the star relation once more. Alright. So, here our assumption now is that x n converges in the sense of convergence in probability to the random variable x. But however, we can appeal to the continuous mapping theorem for convergence in probability. So, this was discussed earlier in week 4 in theorem 1. So, this will tell us that f of x n must also converge in the sense of convergence in probability to the limit random variable f of x. However, if you assume that the given function small f is bounded, then there exists some m positive such that modulus of f of x will be dominated by m for all small x on the real line. And therefore, if we apply this bound to this sequence of random variables f of x n, all these random variables are now bounded by m uniformly across all n. And similarly, the limit random variable that we want to look at, that also is bounded uniformly by this same bound. So, we can use the same bound, and then what we do is that we go back to an improved version of the dominated convergence theorem, which we proved earlier in week 3, the theorem 2 of week 3. If you have a bounded sequence of random variables uniformly bounded converging almost surely to a limit random variable, then the corresponding expectations converge. However, we had improved that in our discussion in week 3 to this fact that if we relax the assumption of convergence to convergence in probability, but retain the uniform boundedness, then we will be able to again show that the corresponding expectations converge. So, that is what we had discussed earlier in week 3, and this is what we are going to apply. Let us see. So, what we have here is that f of x n converge in the sense of probability to f of x, and all these random variables are bounded uniformly by m, and therefore, we must have a L1 convergence, which essentially implies the relevant convergence for expectations. Therefore, we have ensured corresponding expectations converge to the correct expectation, and hence this, since this is an equivalent condition for the weak convergence, our proof is complete. So, what we have ensured is that under convergence in probability, we will have weak convergence or convergence in law or convergence in the sense of distribution. But if we now consider this type of convergence for a sequence of random variables defined on the same probability space, we can actually extend one of our earlier remarks that was mentioned in week 3 and compare all 4 modes of convergences. Here recall first that we had pointed out that convergence in the sense of LP as well as almost sure convergence implies convergence in probability. So, this was already observed in our discussion in week 3. However, we have just now extended this comparison by saying that convergence in probability also imply weak convergence. So, here the weak convergence is the weakest out of all these 4 modes of convergences when we are considering a sequence of random variables defined on the same probability space. Now, we can ask what about the opposite direction. So, we already know that from convergence in probability, we cannot improve in general to either of convergence in LP or to almost sure convergence. However, we can ask the opposite direction about going from weak convergence to convergence in probability, and this is our next result, that we actually have a very partial converse to this earlier proposition, that under certain special conditions we can show that weak convergence implies convergence in probability, but we will discuss that in general the converse may not be true. The result that we are going to discuss is only going to be true under very special circumstances, that weak convergence for a very specific type of sequences will imply convergence in probability. But again, just to repeat, in general we will not have the corresponding statement. Let us see this statement. So, we are saying that we have a sequence of random variables x n defined on a single probability space, and suppose that all these x n's converge in the sense of weak convergence to a constant random variable c. So, here either you treat it as a constant random variable, or you can also treat this constant random variable as a degenerate random variable supported at that constant c. Now, the conclusion that we are going to draw is that the convergence actually happens in the sense of convergence in probability. So, if you have a sequence of random variables defined on the same probability space, and if they converge in the sense of weak convergence to a constant or a degenerate random variable, then this is also going to be true in the sense of convergence in probability. So, let us see how we can establish this convergence in probability. So, to do that, what we need to show is that for any arbitrary epsilon positive, this quantity should go to 0 as n goes to infinity. Let us first get some estimates for this probability. What we first observe, that this event that we are looking at, that can be split in terms of 2 separate events. The first event is when x n takes values strictly less than c minus epsilon, and the other event when x n takes value strictly greater than c plus epsilon. The union of these 2 events is going to give us the event appearing on the left hand side, and since the 2 events that we are considering on the right hand side are pairwise disjoint, I just appeal to the finite additivity of the underlying probability measure and get this equality as written here. But now let us now look at the individual events and their probabilities that appear on the right hand side of the expression. Now, the first probability that we are looking at can be dominated from above by considering an additional equality in the event. So, this is just a very basic manipulation. On the other hand, the second probability that we are considering is actually appearing as the complement of the event x n less equals to c plus epsilon. Therefore, we can write the original probability as 1 minus the probability that x n takes values less or equal to c plus epsilon. However, we now note that these probabilities can be expressed in terms of the distribution function of x n. So, now what we are observing is that the expression turns out to be f of x n, the distribution function of x n evaluated at c minus epsilon plus 1 minus the distribution function of x n evaluated at c plus epsilon. So, therefore, the probability that we are starting with on the left hand side, this quantity can be dominated by certain expressions involving the distribution function of x n. So, this is the inequality that we mark by star and we will come back to this relation star. But before that, let us focus on the weak convergence that we have assumed. So, here we are assuming that we are looking at the degenerate random variable c as the limit, and here the degenerate random variable c has the distribution function given by this, where as soon as x is less than c, the distribution function takes the value 0, if x is greater or equal to c, it takes the value 1, and it has exactly one jump point at the point small c. So, except this jump discontinuity, we must have the corresponding sequence of distribution functions converging pointwise. So, therefore, we must have except the point c, which is x not equal to c, we will essentially end up with two cases when x is less than c and greater than c. So, as soon as x is less than c, we must have the pointwise limit of the distribution functions being 0, and as soon as small x is greater than c, we must have the limit of the distribution functions pointwise being 1. So, therefore, we have explicitly these two values on two different situations. However, if we look at the point c minus epsilon, that is strictly less than c, and therefore, this limit must be 0. If we look at the point c plus epsilon, that is strictly greater than c, therefore, this limit must be 1. Therefore, if we go back to our earlier star relation, so then what we had obtained was certain expressions in combinations with f of x n's. So, on the right hand side you observe that the distribution functions evaluated at c minus epsilon, they converge to 0. The distribution functions evaluated at c plus epsilon, they converge to 1. Therefore, the whole expression on the right hand side of the star relation goes to 0. However, since this is an upper bound given by the probability in question, so therefore, the corresponding probabilities must also converge to 0. So, this is the important application of weak convergence that we are using, and here we have explicitly used that the limit random variable is degenerate and use the exact structure of the limit distribution function. But here we have that since epsilon is arbitrary and these probabilities converge to 0 as n goes to infinity, we immediately conclude that convergence in probability holds, that is, the sequence of random variables converge in the sense of probability to the same constant or degenerate random variable at c. So, in this lecture we have looked at some of the important properties of weak convergence. The highlight was that the weak limit that we are considering has certain uniqueness properties, and if we compare with other earlier modes of convergence, then the convergence in probability implies weak convergence and the corresponding converse holds only under special circumstances. We are going to see certain additional examples later on which will establish that in general we cannot improve the convergence in the sense of weak convergence to the convergence in probability. All right. So, we stop here and we will continue the discussion next time. Thank you.